Now we're going to consider what happens if we take a conductor and we maintain some potential or voltage across the two ends of the conductor. So as you can see here, I have sort of a bar, which is our conductor in the middle, and we have some wires which are connecting that to our battery, which has some voltage V, and we're assuming that these wires have no resistance, so they're ideal wires. And so we can make things a little bit easier by assuming that this bar or this conductor has some constant cross-sectional area given by S. And so let's go ahead and specify a couple other things. We can say the length of this bar is L. And of course, if we have our voltage in this direction, then that's going to induce some electric field across this material, which is going to be from the direction left to right. So we also should know that with our voltage in this applied with this orientation, we're going to have a current coming out of the positive terminal of our battery, going through our conductor, and then returning to the negative terminal. So one other thing, of course, if we're talking about electron movement in this metal, that's going to be moving in the opposite direction of our electric field, so going from right to left. So in this case, because our conductor is not isolated, our electric field is not going to be zero inside of our conductor. So for this case, RE is not equal to 0 inside our conductor. And so the reason for that is that we're not allowing it to reach static equilibrium. So our V doesn't let the system reach static equilibrium. So we can think about these charge carriers in there are trying to get to those surfaces, and if we didn't have anything connected, we'd have this surface over here being negatively charged and this surface positively charged. But of course, once those charge carriers are reaching those surfaces, they're continuing out through these wires and they're being cycled through our system. So because of that, our electric field in the system is going to be this constant value E for a constant voltage, and of course that's going to be some non-zero value. So again, like I said, if we have some uniform cross-section S, so let's say that's uniform cross-section, and so I've drawn this as a circular conductor, but of course we could have other shapes as well. And let's also assume that we have some uniform E. So let's assume in this case we have a uniform electric field. So if that's the case, then our electric field, or the magnitude, is just going to be equal to voltage divided by the length of that conductor. Then what we can do is we can use our point form of Ohm's law. So remember, our point form of Ohm's law was J is equal to sigma times E. And so what we have then is our J, current density, is going to be the current I divided by that cross-sectional area S, which is equal to sigma times V over L. Okay, so now let's say we're interested in finding the resistance of the conductor. So of course, resistance we know is defined as V over I. So that's going to be equal to, plugging in from our equations above, L divided by sigma times S. Okay, and so we can rearrange this, or rather define a new parameter here, and we can say this is also equal to rho sub C times L divided by S. And so these are going to be sort of relatively simple equations, and again, you've probably seen this before in an introductory physics course, but these are for the cases of uniform cross-section and uniform electric field. So this is resistance, of course, for our conductor. And the important sort of qualifier here is that this is for the case of uniform cross-section. So we can sort of think of this as the simplest case that we can consider. And let me go ahead and explicitly define as well this rho C, so we can see it's equal to 1 over sigma, and so we might recognize that as our resistivity. And so resistivity typically is going to have units of ohms per unit distance. So, of course, we're not always going to have this ideal case of uniform cross-section and uniform electric field, and so we're going to come back and we're going to deal with that later if you want to sort of see the general setup for it now before we get to that, you can look on page 183 in the textbook. And again, that's going to be how do we deal with non-uniform cross-section. But sort of as a brief overview to that, what we're going to end up doing is we have to go back to sort of basic definitions of V and I in terms of our integrals and our electric fields, and things get a little more complicated, of course. Also on that page 183, something else to look at is it covers from those sort of more complicated forms our Joule's law, which is how we get our more familiar power equation, so how we get P equals IV. So not something that we're going to be dealing with, but if it's something that's interesting to you, then definitely go check out page 183.